Hey, hello, welcome. In this video, we're going to cover some introduction material to chemistry. Let's begin with some definitions. Chemistry is the study of matter and the changes that matter undergoes. Matter is anything that has mass and occupies space. Everything around you is made of matter. Your pencil, computer, cat, even you and I are made of matter. Matter is made of different combinations of about 100 elements, but don't worry about that right now. Atoms are the smallest building blocks of matter. Molecules are two or more atoms joined together in a specific way. For example, water is made up of 2 hydrogen atoms and 1 oxygen atom joined together. Now, what are pure substances? A pure substance, which is sometimes just called a substance, is matter with very specific properties and composition that doesn't change from sample to sample. For example, let's take a look at a bowl of water. If I scoop up some water from the left side of a bowl, and then I scoop up some water from the right side of the bowl, are these two samples different? Has anything changed? No, because they're both water or H2O. They're both made up of the same stuff, or rather, they have the same composition. All substances are either elements or compounds. Elements are basically substances that are made up of only one type of atom. For example, hydrogen is an element because it's only made up of one type of atom, the hydrogen atom. If we had a balloon filled with pure hydrogen, the hydrogen in the balloon is only made up of hydrogen atoms, nothing else. Meanwhile, compounds are substances that are made up of 2 or more different types of atoms. For example, water is a compound because it's made up of 2 different types of atoms, hydrogen and oxygen. Now let's discuss mixtures. Mixtures themselves are not substances, but rather they're made up of different types of substances. A mixture is a combination of 2 or more substances where each substance keeps its chemical identity. For example, if we mix water and aluminum in a beaker, we have a mixture that consists of water and aluminum because water and aluminum are 2 different substances with their own properties. Mixtures can either be heterogeneous or homogeneous. A heterogeneous mixture is a mixture that doesn't have the same composition, properties, and appearance throughout itself. For instance, wood and rocks are examples of heterogeneous mixtures. If we look at different parts of wood or rocks, they may be different from each other. A homogeneous mixture is a mixture that is uniform throughout. For example, air is a homogeneous mixture because air is made up of multiple compounds, but it's evenly spread throughout. Solutions are typically liquids that are homogeneous mixtures, but they can also be solids or gases. Now let's discuss how we can classify matter. Matter is characterized by its physical state and composition, or whether it's an element, compound, or mixture. Let's recall the 3 states of matter: solid, liquid, and gas. I know some of you will rush to the comments and say something along the lines of, but wait, there's 4 states of matter, you forgot plasma, and my response to this is, 1, no one asked, and 2, you're wrong, there's way more than 4. Let's start with gases. Gas molecules are spread far apart and they move really fast. They like to bump into each other and other objects. This means that gases don't have a fixed volume or shape, and they can be compressed and expanded. Because there's so much space, we can compress the gas by squeezing the molecules closer together because there's more than enough room to do that. Liquid molecules are much closer together. However, there's still enough room for the molecules to move around, which is why liquids like water tend to flow. However, unlike gases, there isn't enough room between the atoms for liquids to be compressible. So liquids have fixed volumes and are not compressible, but because they can flow, they don't have a fixed shape. Solid molecules are very close together, so close to the point where they can no longer move freely. They can vibrate a little, but they really can't move anymore. This means that solids have fixed volumes and shapes, and they are not compressible. Note that temperature changes can lead to state changes. For example, if we heat up ice, it can become a liquid. If we heat it up even more, it becomes a gas. Let's do a little bit of practice. How can we classify water at room temperature? To begin, let's determine the state of matter for water at room temperature. Water is a liquid at room temperature. Now let's determine its composition. Is water an element, compound, or mixture? Water is made up of 2 types of atoms, hydrogen and oxygen, so it's not a single element. Now, is it a compound or a mixture? Water has specific properties and its composition doesn't vary from sample to sample, so water is a compound. Let's go over some more vocabulary. Physical properties of matter can be observed without changing the identity or the composition of the substance. For example, color, odor, density, melting point, boiling point, and hardness all are physical properties. Chemical properties are the way a substance may change or react to form other substances. For example, flammability is a chemical property. Intensive properties are properties that don't depend on the amount of sample that's being observed. Some examples are temperature and melting point because these properties don't change, no matter how much of a sample you have. Extensive properties are properties that depend on the amount of sample. For example, mass and volume are extensive properties. A physical change is when a substance changes its physical appearance but not its composition. A chemical change is when a substance is transformed into a chemically different substance. Mass is the measure of the amount of material in an object. Now let's move on to SI units. What are SI units? SI units are the International Science Units, or units that are used internationally for scientific purposes. SI units are based off of the metric system. Now let's begin with the units. Mass is associated with kilogram, which is abbreviated as kg. Length is associated with meters, which is abbreviated with a lowercase m. Time is correlated with seconds, and this is abbreviated as S or SEC. Temperature is correlated with Kelvin, and this is abbreviated with a K. Electric current is affiliated with ampere, or amp, however you pronounce it, and this is abbreviated with an A or AMP. Amount of substrate is affiliated with moles, which is abbreviated with MOL. Luminous intensity is affiliated with candela, or however you pronounce this again, and this is abbreviated with CD. For the record, if I get a pronunciation off, instead of admitting that I don't know how the metric system works, I'm going to say it's just my American accent. Now let's discuss the positive multipliers. We're starting off with peta, which is abbreviated as P, which has a multiplier of 10 to the power of 15. Tera is abbreviated with T and has a 10 to the power of 12 multiplier. Giga is abbreviated with G and has a 10 to the power of 9 multiplier. Mega is abbreviated with M, and this has a 10 to the power of 6 multiplier. Kilo is abbreviated with K, and this has a 10 to the power of 3 multiplier. The base unit just has a multiplier of 1. Now let's move on to the negative multipliers. Deci is abbreviated as D and has a multiplier of 10 to the power of negative 1. Centi is abbreviated as C and has a 10 to the power of negative 2 multiplier. Milli is abbreviated as M and has a 10 to the power of negative 3 multiplier. Micro is abbreviated as a weird looking U and has a 10 to the power of negative 6 multiplier. Nano is abbreviated with an N and has a 10 to the power of negative 9 multiplier. Pico, or pico, however you're supposed to pronounce it, is abbreviated with a P and has a 10 to the power of negative 12 multiplier. Femto is abbreviated with F and has a 10 to the power of negative 15 multiplier. Auto or ATO, however you're supposed to pronounce this, is abbreviated with an A, and this has a 10 to the power of negative 18 multiplier. Zepto is abbreviated with a Z, and this has a 10 to the power of negative 21 multiplier. Temperature is the measure of hotness or coldness of an object. Note that heat always flows from a substance at a higher temperature to one at a lower temperature. Kelvin is the SI unit for temperature. Note that Kelvin does not use the degree symbol, it just uses the letter K. Let's cover some conversion formulas for temperature. Kelvin equals the degrees in Celsius plus 273.15. Celsius equals 5/9 times the degrees in Fahrenheit minus 32. The other way around would be Fahrenheit equals 9/5 times the degrees in Celsius plus 32. Let's discuss derived SI units. Derived SI units are obtained by multiplication or division of base units. For example, speed is meters per second, or meters divided by seconds. The SI unit for distance is divided by the SI unit for time, so speed is a derived limit. Other derived units include volume and density. Let's discuss some basic volume conversions. 1 liter equals 1 cubic decimeter. 1 milliliter equals 1 cubic centimeter. Now, the formula for calculating density is mass divided by volume. This is commonly expressed as grams divided by cubic centimeter or grams divided by milliliters. Note that density is temperature dependent because the volume changes from temperature. Alright, let's do some more vocabulary. Exact numbers are defined. For example, there are exactly 12 eggs in a dozen. This is defined. Inexact numbers are obtained by measurement, which are not defined. Precision is how closely individual measurements agree. For example, let's pretend I weighed an apple on 5 different scales. If the 5 scales report similar numbers, then the precision is good because the measurements agree with each other really well. Accuracy is how closely individual measurements agree with the correct or true value. For example, if all 5 of the scales report a ridiculous number like 500 pounds, my accuracy is off because there's no way a single apple is 500 pounds. In chemistry, we want both good precision and accuracy. So for instance, if all 5 of my scales reported about 0.33 pounds for the apple, I have both good precision and accuracy because 1, my 5 results are similar to one another, and 2, a 0.33 pound apple is an acceptable value, unlike 500 pounds. Standard deviation is used to determine precision. Now let's go back to the 5 weights and the 1 apple problem. Let's take a look at Table 1. Notice that the 5 weights on Table 1 report very similar values. This means that Table 1 has good precision. Now let's take a look at Table 2. Table 2 reports very different values. This means that Table 2 has bad precision. Now, is there a way we can calculate how precise our measurements are numerically? To do this, we can use the following formula. Now, let's break down how this formula works and how we can use it. N represents the number of measurements. So for example, let's take a look at Table 1. Notice how we had 5 scales and we took 5 measurements. So therefore N for Table 1 is 5. X of I represents the individual values. So let's take a look at Table 1 again. The individual values are 0.33, 0.35, 0.29, 0.31, and 0.323. So our individual values are just our results. X, with the line over it, represents the average of the measurements. Another word for average is just mean. So to calculate the average, you would just calculate the mean. S represents the standard deviation. Now, the smaller the number S's, the more precise our measurements are. The larger the number S's, the less precise our measurements are. Now let's do some practice with the tables. First, let's identify what n is. N is the number of measurements. In table 1, we have 5 measurements, so n equals 5. Xi represents the individual measurements. The individual measurements are 0.33, 0.35, 0.29, 0.31, and 0.323. X, with the line over it, I actually don't know what the symbol is called, but I don't care, represents the average of these numbers, or the average of the measurements. Now, to solve for the average, we have to add all of these numbers up and then divide them by the number of measurements, which is 5. So let's solve for the average. 0.33 plus 0.35 plus 0.29 plus 0.31 plus 0.323 divided by the number of measurements, which is 5. Now, let's solve for this with our calculators. You should end up with a value 0.3206. So this equals 0.3206. Now, we can rewrite the formula. Now let's do the math. I've set x of 1 equal to 0.33, x of 2 equal to 0.35, x of 3 equal to 0.29, x of 4 equal to 0.31, and x of 5 equal to 0.323. So now we need to solve for the summation. So let's start with 0.33, or x of 1, minus 0.3206, or the average, squared plus 0.35 minus the same average, 0.3206, and so on. This would be x of 3, 0.29, minus the average, 0.3206, squared, and then repeat the same process for the remaining x values. And now, divide all of this by 5 minus 1. Now, let's plug this into our calculators. You should get something along the lines of 0.0224. So because 0.0224 is such a small number, we have a small standard deviation. So we can say that table 1 has good precision. Now, if we wanted to solve for the standard deviation of table 2, we would just follow the same procedure. Note that these are the new x of I values. If you want to solve for the standard deviation, you can, but I'm not going to do that because I'm too lazy, so let's use a calculator and find the standard deviation that way. Now, let's plug in the 5 measurements. Make sure to select the sample option, because in chemistry we tend to use the sample option. If we choose population, it'll use a different formula, and that'll mess up your answer. So let's press calculate. Our standard deviation for the second table is about 184.54, which is a really large standard deviation, which just goes to show that the second table has bad precision. Let's discuss significant figures. Significant figures are all of the digits in a measurement. The greater the number of significant figures, the more precise the measurement is. Here are the rules for significant figures. 1. All non-zero digits are significant. For example, in the number 46, there are 2 significant figures, because both 4 and 6 are non-zero. 2. Zeros between non-zero digits are significant. For instance, in the number 1005, there are 4 significant digits. 1, 0, 0, and 5 are all significant. The zeros are between 2 non-zero digits, so they're significant. 3. Zeros at the beginning of a number are never significant. For instance, in the number 0.0026, there are only 2 significant figures because the first 3 zeros do not count. 4. Zeros at the end of a whole number are not significant. For instance, the number 550 only has 2 significant figures. The 0 at the end does not count. 5. However, zeros at the end of a number that has a decimal point is significant. For the number 550 with the decimal point, there are 3 significant figures because we have a decimal point. The 0 counts. If we have a number like 100.0, we have 4 significant figures because of the decimal point. The last 3 zeros count. 6. Exact numbers have an infinite number of significant figures. For example, a dozen eggs can be written as 12.00000000 eggs forever because 12 is the exact number of eggs in a dozen. There's an infinite number of zeros after the decimal point because 12 is an exact number. Now, how do we use significant figures in calculations? For addition and subtraction, the final result must have the same number of decimal places as the measurement with the fewest decimal places. Let's do an example problem. 20.42 plus 1.322 plus 83.1 equals 104.842. However, 83.1 only has 1 decimal place. That means we have to make 104.842 only have 1 decimal place. If we round our final answer to the nearest tenth, we get 104.8, which is our result after accounting for significant figures. For multiplication and division, the final result must contain the same number of significant figures as the measurement with the fewest number of significant figures. For instance, let's multiply 6.221 and 5.2 together. We get 32.3492, but because one of the numbers we multiplied, 5.2, only has 2 significant figures, we have to make our final result only have 2 significant figures. To do this, we have to round 32.3492 to the ones place. We will end up with 32 as our final answer. Now let's do a little bit of a math lesson. Dimensional analysis is a method for converting units which can be very useful in chemistry. In dimensional analysis, we start off with the number in a specific unit, and then we multiply it by a ratio to get our desired unit. This ratio is called the conversion factor. A conversion factor is a fraction where the numerator and denominator are the same quantity expressed in different units. For instance, 1 mile over 5,280 feet is a conversion factor because a mile is 5,280 feet. If you think about it, this is really just a ratio in fractional form. Also, note that a conversion factor can be written in multiple ways. So, for example, 1 mile over 5,280 feet can also be written as 5,280 feet over 1 mile. Nothing changes because the ratio is still the same, just written differently. In dimensional analysis, the goal is to multiply or divide units into each other and have equivalent units cancel out. This may be difficult to comprehend through words, so let's do some examples. Now let's convert 2 miles to kilometers with dimensional analysis. The first thing that we should do is write down the unit that we want to convert, which is 2 miles. Then we want to multiply it by a conversion factor. In this case, we want to multiply it by the conversion factor that relates miles with kilometers. 1 kilometer is about 0.6214 miles. Notice how we have miles in the denominator and miles in the numerator. So therefore, we can cancel these units out. So we're left with 2 divided by 0.6214 kilometers. To solve for this, we can just plug it into our calculators. 2 divided by 0.6214 is 3.22. So therefore, 2 miles is 3.22 kilometers. So what we did here was we took a given unit and then we multiplied it with the conversion factor. And then we canceled out the given units, and then our final answer was the desired unit. In this case, the given unit was 2 miles, and the desired unit was in kilometers. Dimensional analysis can be very useful if you want to convert something multiple times to get to a final result. So for example, let's say we want to convert 8 meters to inches. What's the conversion factor between meters and inches? To be honest, I have no clue, but what I do know is the conversion factor from meters to centimeters, and then from centimeters to inches. If we can convert 8 meters to centimeters, and then convert centimeters to inches, then we can still get our final answer. The conversion factor between meters and centimeters is 1 meter is 100 centimeters. The conversion factor between centimeters and inches is 1 inch is 2.54 centimeters. Now let's start by writing out our given unit, 8 meters. Now let's convert this to centimeters by multiplying it by the conversion factor that relates meters with centimeters. Notice how meters is in the numerator. We need the meters to cancel out with the meters here. So meters has to be in the denominator. Recall that with conversion factors, we're allowed to flip the conversion factor. We're allowed to find the reciprocal because they're still the same. The ratio is still the same. So we can multiply this by 100 centimeters over 1 meter. Notice how the meters, they cancel out. Now we can multiply it by the conversion factor that converts centimeters to inches because this entire value is now in centimeters. 1 inch is 2.54 centimeters. Notice how now we can cancel out the centimeters in the denominator and in the numerator. So we're left with 8 times 100 inches divided by 1 times 2.54 in the denominator. To solve for this, we can just plug it into our calculators. You should get something along the lines of 314.8 314.961. So 8 meters is equivalent to 314.961 inches. Now let's do a real chemistry conversion. Find the mass in grams for 2 inches cubed of gold, which has a density of 19.3 grams per cubic centimeter. Something that you may find useful for this problem is 1 inch equals 2.54 centimeters. Feel free to pause this video to try this problem on your own. Now first, let's notice what units the problem is in. We have inches cubed and then centimeters cubed. So let's do a little bit of algebra and cube both sides of this equation. So 1 cubic inch is equal to 16.39 cubic centimeters. So our conversion factor is 1 inches cubed over 16.39 cubic centimeters. Now let's analyze the problem a little bit more before we start. Notice how we start with inches cubed, and then we want to end with grams. This is a conversion factor that's been given to us. Notice how the final answer should be in grams, so 19.3 grams should always stay in the numerator. But notice how in order to get grams, we have to first convert inches cubed to centimeters cubed. To do this, we can use this conversion factor. So let's start with the given unit. Now let's multiply this by the conversion factor. Unfortunately, the inches cubed is in the numerator, but recall that with conversion factors, we're allowed to flip the fraction because the ratio stays the same. So let's multiply this by 16.39 centimeters cubed over 1 inch cubed. Notice how we can cancel out the inches cubed in the denominator and in the numerator. Now that we have this value in centimeters cubed, we can multiply it by the conversion factor that's been given to us. So let's multiply it by 19.3 grams per cubic centimeter. Notice how we can cancel out the cubic centimeter in the denominator and in the numerator. Now we'll end up with 2 times 16.39 times 19.3 grams over 1 times 1. To solve for this, let's plug it into our calculators. You should get something along the lines of 632.654. So the mass for 2 cubic inches of gold is 632.654 grams. This is your final answer.